Chapter 1. Perfect Numbers and Digital Roots. Introduction. In the big world of math, there are some really cool things that have fascinated mathematicians for a very long time. One of these cool things is called a perfect number. Perfect numbers are special because if we add up all the numbers that divide into them evenly except for the number itself, we get the original number back. For example, 6 is a perfect number because its factors, 1, 2, and 3, add up to 6. Another interesting thing in math is called the digital root. The digital root of a number is the single number we get after adding up all the digits in that number over and over again until only one number is left. For example, to find the digital root of 56, we add 5 and 6, which gives us 11. Then we add 1 and 1, which gives us 2. In this video, we will prove that the digital root of all perfect numbers, except for 6, is 1. Don't forget to subscribe to our channel for more educational content. Chapter 2. The general form of perfect numbers. To understand why the digital root of most perfect numbers is 1, we first need to understand how perfect numbers are formed. Every perfect number can be written using a special formula that uses prime numbers. This formula is 2 to the power of p minus 1, multiplied by 2 to the power of p minus 1 in parentheses, where p represents a prime number. For example, if p is 3, then 2 to the power of p minus 1 becomes 2 squared, which is 4. 2 to the power of p minus 1 means 2 multiplied by itself p times minus 1. Using our example of p equals 3, 2 to the power of p minus 1 becomes 2 to the power of 3 minus 1, which is 7. The cool thing about this formula is that it can create a perfect number for every prime value of p. For instance, if we plug in p equals 2, we get 2 times 3 equals 6, which is the first perfect number. In the next part, we will learn about something called Modulo 9. Chapter 3. The interesting properties of Modulo 9. In Modulo 9 arithmetic, we only care about the remainder after a number is divided by 9. For example, 16 modulo 9 would be 7 because when we divide 16 by 9, we have 7 left over. Similarly, 25 modulo 9 would also be 7. The digital root of a number is the same as the number itself modulo 9. For instance, the digital root of 16 is 7, 1 plus 6 equals 7, and 16 modulo 9 is also 7. This fact will be helpful when we prove our statement about the digital root of perfect numbers. Chapter 4. Digital root and modulo 9. A special relationship. We can find the digital root of a number by finding what's left over when we divide it by 9. To prove that the digital root of most perfect numbers is 1, we need to see what happens to this expression when we reduce it modulo 9. We need to look for patterns in the remainders when 2 to the power of p minus 1, multiplied by 2 to the power of p minus 1 in parentheses, is divided by 9 for different prime values of p. In the next part, we will start our analysis by plugging in different prime values for p in the general form of perfect numbers. Chapter 5. Exploring Mersenne primes. Mersenne primes are prime numbers that can be written in the form 2 to the power of p minus 1, where p is also a prime number. The expression for Mersenne primes, 2 to the power of p minus 1, appears in the formula for perfect numbers, 2 to the power of p minus 1 times 2 to the power of p minus 1. Every perfect number has a matching Mersenne prime. For example, for p equals 2, 2 to the power of p minus 1 equals 3, which is a Mersenne prime. And as we know, 2 times 3 equals 6, which is a perfect number. Understanding Mersenne primes helps us focus on the properties of the expression 2 to the power of p minus 1 modulo 9. Chapter 6. Proof for p equals 2, the first perfect number. Let's start by plugging in p equals 2 into the perfect number formula, 2 to the power of p minus 1 times 2 to the power of p minus 1 in parentheses. This gives us the first perfect number, 6. The digital root of 6 is 6, which is different from the general rule that the digital root of perfect numbers is 1. When we divide 6 by 9, the remainder is 6. Although this case is special, it helps us start our analysis. Chapter 7. Proof for p equals 3, uncovering the pattern. We'll continue by plugging in p equals 3 into the perfect number formula 2 to the power of p minus 1 times 2 to the power of p minus 1 in parentheses. This will give us the perfect number 28. Let's calculate the digital root of 28. 2 plus 8 equals 10. 1 plus 0 equals 1. So, the digital root of 28 is 1. Let's see if we get the same answer using modulo 9. First we calculate 2 to the power of 3 minus 1, which is 7. Next we calculate 7 modulo 9, which is also 7. Finally we multiply 7 modulo 9 by 4 modulo 9, which gives us 28 modulo 9. Since 28 divided by 9 has a remainder of 1, we know that 28 modulo 9 is equal to 1. Chapter 8. Proof for p equals 5 and p equals 7. Solidifying the theory. For p equals 5, the perfect number formula will give us 496. The digital root of 496 is 1. 4 plus 9 plus 6 equals 19. 1 plus 9 equals 10. 1 plus 0 equals 1. Using modulo 9 we can confirm that 496 modulo 9 is also equal to 1. Similarly, for p equals 7, we get the perfect number 8128. The digital root of 8128 is 1. 8 plus 1 plus 2 plus 8 equals 19. 1 plus 9 equals 10. 1 plus 0 equals 1. Through these examples we see a pattern. This trend shows a deeper relationship between the digital root of perfect numbers and modulo 9. Chapter 9. Generalization for all prime numbers. P. Based on what we saw in the previous examples, we can say that for any prime number p greater than 2, the digital root of the corresponding perfect number is 1. This is because 2 to the power of p minus 1 modulo 9 will always give us a remainder that, when multiplied by 2 to the power of p minus 1 modulo 9, will result in 1 modulo 9. This repeating pattern, along with the properties of prime numbers, ensures that the perfect number expression will always reduce to 1 modulo 9. This shows the amazing connection between perfect numbers, digital roots, and modulo 9. Chapter 10. A special case. Why 6 is different. The reason 6 is different is that the prime number 2 is special when used in the perfect number formula. When p equals 2, the expression 2 to the power of p minus 1 becomes 2 squared minus 1, which equals 3. 3 is a prime number, but it is also a factor of 9, the number we are using for modulo. This special case shows how important the number we use for modulo, 9 in this case, is, and how it interacts with the specific prime numbers in the perfect number formula. Chapter 11. Conclusion. Unveiling the beauty of mathematics. We have proven that the digital root of all perfect numbers, except for 6, is 1, showing us a cool pattern hidden within this mathematical formula. Our journey took us through the general form of perfect numbers, the uniqueness of modulo 9, and the importance of Mersenne primes. The special case of the perfect number 6 shows us the complexity of this relationship and reminds us that there are always new things to learn and explore in math. As we continue to explore the mysteries of math, we will surely find more amazing things and interesting connections that will keep us interested and excited.